Can everyone see the screen?
Yeah, we can see.
Okay, perfect. All right, well, thanks for the invitation to speak, and I hope everyone is doing well during these times. So today I'm going to talk about a new way to solve multi-matrix models in the large N limit. So let me start by defining what I mean by solving a matrix model. So for our purposes, a multi-matrix model, so in this case we have just two matrices, is defined by an integral of this form, where V is some polynomial in A and B, and the measure here is the uniform measure over all Hermitian matrices. More generally, we want to consider expectation values of some observables, which are also polynomials in A and B, the random matrices. Now, if you just meet an expression like this out in the wild, it's not clear whether or not these integrals should even exist. So this is in contrast to the case where you just have a finite and matrix integral, in which case whether or not the potential is bounded or unbounded pretty much determines whether or not the model exists. But in the large N limit, it's actually not clear a priori whether a typical polynomial of the form v of A and B will actually give a well-defined model. So the zeroth order question that we can ask is whether or not these expressions exist. And of course, the first order question that we want to answer is to determine the actual values of these numbers as a function of couplings, when the couplings exist, when the models exist. And let me emphasize that even the zeroth order task is very difficult in general. Both the zeroth order question and the first order question have been answered completely in the case of single matrix models, but a subset of multi-matrix models of measure 0 actually has been solved. So even for a two matrix model, we can't typically, we know very little about either of these questions. And you might think, well, this is not too bad. We can just Monte Carlo this matrix integral. But in fact, in the cases where the potentials are unbounded, it's not clear that Monte Carlo simulation will work. Or if it does work, it will have to be very subtle. And that's because the measure for any finite to n is not going to make sense. Okay, so if we're going to make progress on this type of question, especially if we're going to push the models to a regime where the potentials are unbounded, we will need an approach that works directly at large N. Okay, and this is an approach which I will discuss today. Now, just some motivation and some outline before we begin. So first, I'm going to review the so-called old matrix story. This is the sort of earliest version of holography, perhaps, where there's a connection between string theory and matrix integrals. And I'm sure many of you are very familiar with this. This is mostly an appetizer for why we would care about matrix integrals in this form, and especially why we would care about pushing the integrals into a regime where the couplings are such that the potential is unbounded. Then I will explain the method. And in order to do that, there are sort of two little prerequisites. One is to explain the loop equations in the multi-matrix model. And the second is to explain what sort of positivity requirements a given matrix integral has to satisfy. So combining those two ingredients, I will invent some sort of algorithm that you might call the matrix bootstrap. And then I will discuss some applications of this bootstrap, first to single matrix models where we completely understand the physics and they can be analytically solved, and then to some multi-matrix models where it's very difficult or impossible to solve these models analytically. So first, the appetizer, why should we care about these matrix integrals? The oldest reason kind of goes back to Toft in 1974, where he explains that these integrals, or more generally field theories of this form, have a very special feature, and that is that their perturbative expansion becomes a topological expansion. And to leading order in 1 over n, the dominant contribution to, say, the partition function comes from the planar diagrams. Okay, so this is some picture of a particular planar diagram using the double line notation. But more generally, there's some connection between matrices and string theory And that's what I'm now going to explain in the context of the simplest possible multi-matrix model. And that's so-called Ising matrix model, or the two-matrix model with A-B interaction. And this model is completely integrable, but let me explain its connection with the Ising model on a random planar surface. Okay, so the idea is that we're going to try to analyze this model by just doing standard perturbation theory. So Talks told us that we should just focus on the planar diagrams. So in this model, we have a cubic interaction. So we're going to draw planar diagrams which have 3 edges coming out of each vertex. And here's one such example. Right now, once we have this planar diagram, we actually have 2 types of vertices possible, right? There's a vertex, the GA, in this equation, and there's also a B vertex, the GB, in this equation. Okay, so when we have these 2 types of vertices, we should label each vertex as either GA or GB, GA or GB, right? And let's say that we take the rule that whenever we label one with a GA, we're going to put a minus sign. And whenever we put a GB, we're going to put a plus sign. And it's clear that we should sum over all possible choices of plus and minus, right, on this graph. Okay, so when we do that, we have one additional rule, which is that whenever there's a plus next to a minus, right, there's a plus next to a minus, we have to use a propagator that joins an A next to a B. And that propagator is given by this coupling constant C. On the other hand, if the plus is next to a plus, or if we have a minus next to a minus, then we're going to just use the standard propagator here, which is 1. So in conclusion, when we do the perturbative expansion, we're going to get some perturbative expansion in these GAs, GBs, and Cs. And whether or not the pluses and the minuses are chosen and how exactly they're arranged will determine the value of this number right here, right? It depends on the number of vertices of the A type, the number of vertices of the B type, and the number of edges between A's and B's, and the number of edges between like spins, right? So in general, the idea is to interpret this number here as the Boltzmann factor for the Ising model. So for example, whether or not there's a plus or minus, that's the cost of putting 2 spins of different type next to each other is determined by this propagator C. Okay, I hope that was somewhat clear. The main key point is that the perturbative expansion, the ordinary Feynman diagram expansion, becomes reinterpreted as a sum over field configurations. And the field configurations in this case are the spins. And if we go to the limit, if we push to a limit where the Ising model becomes critical, we go to the critical temperature, then we will have a CFT, right, coupled to a planar diagram. Furthermore, if we, well, strictly speaking, what we also need to do is we need to make the planar diagram extremely large. So we need to tune both the G's and the C's so that the planar diagram becomes extremely large and the typical planar diagram in the sum becomes extremely large, and we need to tune the value of C so that the Ising model is pretty much very close to the critical point. And if we do this, we will get some theory which is well described by the so-called Ising model. It's one of the minimal model CFTs, and it's coupled to Louisville gravity. That's the sum over these planar diagrams becomes a sum over the metric, roughly speaking. Okay, so this was just an example of how a 2-matrix model with some additional tuning can give you some sort of string worldsheet or some 2D quantum gravity with some matter degrees of freedom. And more generally, if you had some general interaction between 2 matrices or maybe more matrices, you would expect to have some other degrees of freedom, perhaps in some more complicated CFT if you tune to the critical point. And well, this was studied for several decades ago. People understood this quite nicely, but the progress stopped because one of the reasons that there were some, one of the shortcomings of this sort of program was that we weren't able to solve models besides a very special models, basically of the AB type interaction and small variants of that. A typical interaction which might involve AB, 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 or A cubed, B cubed, AB in this potential is not integrable as far as we know. So we don't know how to solve those models and whether or not they correspond to some interesting world sheaf theories. Okay, so now that was the motivation. One motivation for solving these matrix models might be to try to understand whether a more complicated matrix integral gives you some other type of string world sheaf theory, or gives you another way to get, say, one of the minimal models coupled to Liouville gravity. Now I will explain the two sort of ingredients that go into the new approach to solving these multi-matrix models. So the first ingredient is the loop equations. The loop equations are nothing but the Schwinger-Dyson equations, just applied to this large N matrix model context. Okay, so as Schwinger-Dyson equations, they can be derived by this sort of standard trick of integrating a total derivative, right? And here you're allowed to put any combination of A's and B's that you like. And when the derivative d by dA acts on this object, it will produce two terms, depending on whether or not it acts on the O or whether it acts on the action, right? So this can be diagrammatically interpreted as follows. So here I've just, the diagram corresponds to the simplest possible single matrix model, which is just the single matrix model with a cubic potential. And the idea is you want to compute some correlator, say a trace of m to the k, right? You follow one of the external lines into the blob. Now, when the line enters the blob, there are two possibilities. The line can either never encounter a vertex, in which case it just comes out the other side as one of the other external lines. That's possibility one. Possibility two is that it encounters a vertex. Now, for possibility one, we know something more because it's a large N theory. We know that we're dominated by planar diagrams. So in particular, what that tells us is that if it never encounters a vertex, it has to split the diagram into two pieces. And there cannot be lines, for example, that go from this blob to this blob, because then it wouldn't be a planar diagram. So this term here, this term with the two blobs, will give us a double trace term. And because of large N factorization, as I just explained, it will just be a product of the single traces. So this gives us a closed relationship between higher point correlation functions and lower point correlation functions. And in general, it's a series of quadratic equations that we have to solve in all of the variables. The variables in this case being single trace correlation functions. Now, the multi-matrix generalization of this is very simple. You just basically add different colors corresponding to the different matrices. So for example, you follow in this blue line, right? And it can either connect to one of the blue lines or a different blue line, but it can't connect to a red line unless there is some interaction vertex, which allows a blue matrix to become a red matrix. Right? Yeah, so this is just the same model. The diagrammatic interpretation of the loop equations is the same, except here we have a squared b interaction instead of just the a cubed interaction. But you see that the structure is quite similar. Okay, now I just wanted to emphasize one sort of property of this loop equations that we're going to be seeing a lot of in the future. So the property is the so-called search space. The search space is basically the set of initial conditions to the large N loop equations. The large N loop equations, as I've already said, they relate the low point correlation functions to higher point correlation functions. So if you know some of the low point correlation functions to begin with, you can generate more and more higher point functions. And the question is, what is a minimal set of correlators such that if we knew these, the loop equations would fully determine the rest of them? All the infinitely many correlation functions would be determined from this minimal set. And sort of a basic question is just whether it's finite or infinite, right? For the single matrix model, it's rather clear. I will discuss this a little bit more in a sec, but in the single matrix model case, the dimension of the search space is just determined by the degree of the polynomial which appears in the interaction terms. And you can understand this just by looking at the loop equation that I displayed previously. Essentially, when you have a potential of degree d, you won't have in the initial loop equations, you'll be missing some correlation functions. So you need to know those first before you determine the rest of them. Now for the M matrix model, where M is greater than 1, it's rather complicated to get a precise counting of the dimension of the search space. But we can have a crude estimate of what the dimension is using the following argument. So the idea is to count the number of correlation functions of degree k, for example. So for degree k, there are m to the k over k roughly correlation functions. The reason why you divide by k is because there's a cyclicity property in the trace, right? So trace of a, b, c is the same as trace b, c, a. So this reduces the number of single traces by roughly a factor of k. The precise counting is a little bit more subtle. However, the number of loop equations at a given degree k is not just the number of correlators, but it's actually k times that. And the reason is, when we explained the loop equations a minute ago, you saw that we could enter the blob using any one of the vertices, any one of the edges, and we would get a separate loop equation, right? Once again, like if you look at this blob, right, you could enter the vertex, enter this blob using any of the different edges, and that would naively give you a different loop equation. So that means that the number of loop equations that we roughly have for a finite degree is just m to the k. It's m to the k over k times k. On the other hand, the number of variables that we introduce when we relate lower point functions to higher point functions is m to the k plus d over k plus d, right? Where d is the degree of the polynomial that we are interested in. So in general, what this tells us is that if you make k large enough, you will have enough constraints, roughly, at least just from the parameter counting, you'll have roughly the right number of constraints so that you expect to be able to solve for all the correlation functions. So this suggests, at least, the precise counting is a little bit complicated, but at least it suggests that the dimension of the search space is finite, even for a multi-matrix model, and even for a fairly generic multi-matrix model that we may be able to say very little about in terms of the analytic solution. Okay, let me now explain the positivity constraints. So the question is very simple. If I hand you a list which purports to be a list of correlation functions of a large N multi-matrix model, how can you tell if I'm lying? Okay, so in particular, if the list, say, if I tell you that the list is supposed to be trace m, m squared, m cubed, m to the fourth, etc., one simple test that you could just do is check that all the even moments that I gave you are positive, right? It's obviously impossible for a Hermitian matrix to have trace m squared be negative. So that's one simple test, but are there more sophisticated positivity requirements that these matrices have to obey? And the answer is actually quite simple. The answer is that if you take an arbitrary superposition of matrices raised to arbitrary powers, so in this case, let's focus on the single matrix model first, right? Then this combined matrix, this superposition of matrices, has to satisfy the equation trace of phi dagger phi is greater than 0, right? That just follows from the inner product of matrices. That in turn tells us that if we form this matrix of correlators, cal m, where cal m, the entries of cal m are themselves correlation functions of the matrices, that this object here should be positive semi-definite. That means all the eigenvalues of the matrix have to be positive. Okay, so that is certainly one condition that these matrices have to satisfy, even in the large N limit and so forth. Now, to generalize this to multi-matrices, we just need to consider phi not to be just powers of one particular matrix, but it's clear that we're allowed to take arbitrary linear combinations of any words or strings formed out of all possible combinations of A and B, right? And as we already have been discussing, there are exponentially many of them because you can put A's and B's in many different orders. Okay, so, oh yes, this is related to some interesting 20th century mathematics, which I just learned about recently. like you, I probably haven't heard of the hamburger moment problem, but I looked up on Wikipedia and I found this article which says, given a list of numbers which purports to be the moments now of a ordinary random variable, what are the necessary and sufficient conditions on this list such that we're guaranteed that there exists some sort of measure, positive measure, so that the moments, such that this list are the moments of the distribution. And you see that this is closely related to the previous problem. In particular, in the single matrix case, you can think of trace of m to the k as the expectation value of some random variable, where the random variable is the eigenvalue of the matrix, right? So in particular, in the single matrix model, we can think of the large n solution is basically just describing the eigenvalue distribution of the matrix, right? And that eigenvalue distribution defines some sort of measure, and the various traces just become the moments of that measure, right? So the necessary and sufficient conditions for a problem, for this sequence to have a moment, to be the moments of a measure, has been well explored in 20th century mathematics. And the necessary and sufficient criteria are indeed what I just stated before. Now, it's an interesting question, I think, to generalize this to the multi-matrix case, where we're sort of asking for a non-commutative version of the hamburger moment theorem. And in particular, if you start asking, you can ask more refined questions. So you can ask whether, if you truncate the moments, so I don't give you all infinitely many moments, I just give you the first 1,000 moments of some distribution, whether or not that list, so what are the necessary and sufficient conditions for that list to be given to be the moments of some random distribution? That is a rather subtle question, apparently, especially in the case where they're multivariables and they can be non-commutative. But it's clear that these are at least necessary conditions that the distribution has to satisfy. Whether or not they're sufficient is a matter of is a different story. Okay, now before I get into applications, I think it'd be a good time to pause for questions if there are any.
Yeah, I have a question. Could you slide slide back?
Yes.
So imagine the space of X is discrete. So we have only a finite set of X's. Then the function, the space of function, no, keep going. Where you wrote this thing about the hamburger.
Yes.
Right. So imagine X takes finite values, and then U of X also takes finite values, and then this is just a linear problem, isn't
it? Yes, I agree.
And so so is the issue that X is a continuous variable, or that the range is infinite? What's the point?
Well, I don't think there's no issue in the case where there's a single variable, but yeah. Well,
it doesn't matter how many X's there are, because if X is finite set, then you can call it 2 variables, 3 variables, doesn't matter. And the value of the function at X and Y is an unknown. You compute some moments. It's a linear combination of these. And if you know the moments, you can solve for the value of the function. So there must be some more elements here.
We want the result to be positive.
Yeah, we want mu to be positive, but
you can certainly solve for mu. Say if you truncate the finite dimensional version, you can solve for mu, but what you want to know is in advance whether the solution is going to be positive. And you want to phrase this condition in terms of these moments.
Yeah, I mean, this problem is, like I explained, I think it's fine in the case where, well, you see, why I'm hemming and hawing is because I don't know how to translate the multi-matrix version of this problem into a statement like this, right? Because, you know, in the single matrix case, there's the eigenvalue distribution, but in the multi-matrix case, there's no simple function which characterizes all the traces of A's and B's, right? So I don't know, that's the sort of 0th order problem, which I don't know how to translate, but yeah. Yeah, for the hamburger moment problem, the solution is just that as long as this matrix cal-m has, which is defined by the, this expression here, as long as this matrix is positive semi-definite, then you're guaranteed that there exists some positive measure mu such that you can solve this problem. Yeah, I'm not sure. Maybe that. Yeah. Okay. Well, let me now discuss the applications of this idea to the single matrix case first. Of course, in the single matrix case, we know the exact solution to pretty much any problem that we're interested in. Here, especially at large n, right? And here, I'm just studying the simplest case, which is potential, which has a quartic term. And we're looking at trace of m squared as a function of the coupling G. Okay, so as G increases, this potential becomes more confining, and therefore the trace of m squared goes down, right? And this green line is the exact solution that we get from solving using the usual methods. Now, if we, instead of trying to solve it exactly, we just apply the previous philosophy where we take trace m squared as the search space, and then we generate all possible values. We generate all possible correlation functions based on an initial guess of trace m squared. And then we check whether the resulting matrix is positive semi-definite. We will get some shaded area where inside this shaded area, the matrix cal-m is positive semi-definite, and outside it's not. Okay, and here the point of this plot is just that as we increase the number of constraints, the region becomes smaller and smaller. So there's the gray region and then the black region, which I think comes from like 8 or 10, considering matrices which are like 10 by 10 or 20 by 20. So it's relatively small matrices, and you can see that it's converging extremely well to the exact solution. Okay, so this is something you can do on your computer in like 5 seconds, right? You just need to
the size of the matrix. Sorry.
Say again?
The size of the matrix that you're talking about is this cal-m that you checked.
Yes, the cal-m. Yes, okay. Yes, exactly. Yeah, we shouldn't confuse cal-m with the actual matrix, the random matrix m, which is infinite dimensional. Yeah. So in particular, cal-m, just practically speaking, right, the loop equations are some quadratic equations, so we can solve for the entries of cal-m in terms of trace m squared, and they're just some polynomials in m squared, trace m squared. And we're just asking whether this matrix, this like 20 by 20 matrix is positive semi-definite or not. So if we want to look under the hood a little bit and see sort of what constraints are activated, we can do so. So here are some plots where we just enforce a few constraints or single constraints at a time. So this purple line here is just coming from the constraint that trace of m to the 8th is positive. And this orange line and blue line are trace of 72, m to the 72 and trace of m to the 68 are positive. So you see that there's some sort of interesting structure, and that's because, well, if you, for example, compute the determinant of, well, yeah, okay. In this case, it's actually a bit simpler. So trace of 68 is just some polynomial in trace of m squared, right? So it crosses the 0 axis several times, and that's why you have some of these sort of finger-like structures in this graph. And where it crosses the 0 axis is dependent on the value of the coupling. Okay, something slightly more interesting is when we try to push G to a negative value of the coupling, right? So we can also try to see what the constraints look like in that case. And in that case, we get these different shades of gray correspond to enforcing more and more constraints, right? And what we see is that, well, I haven't plotted it here, but if we put all the constraints, we would again converge exactly to the green line. But for some finite constraints, we get some interesting behavior. In particular, notice that that the peninsula closes off at some point, right? And when it closes off, that's telling us that beyond that point, no matter what value of trace m squared we choose, we cannot find a distribution which satisfies the positivity requirements that we want it to satisfy. So in particular, it tells us that the model is inconsistent. And this is actually very nice because we know that this model is not just, is only consistent for values of g that are positive and g's that are negative, but small and negative. Up the radius of convergence of perturbation theory is -1/12, I think, in this model. So if you go beyond that, the model is ill-defined. And in fact, just by looking at these positivity constraints, we can estimate pretty carefully where that radius of convergence is, where the model makes sense. And as we increase the constraints, right, there's a rapid convergence of the tip of the peninsula to the tip of this green line, which is the endpoint at which the model sort of dies. Okay, and this point is also interesting, of course, because if we want to make contact with string theory, right, we need to, as I explained, approach the critical point. So it's sort of interesting that just by doing these constraints at relatively low order, we can quickly and easily extract this point here. Sort of interesting other sort of phenomena that can happen in single matrix models is when you have multi-cut solutions. So this corresponds to, for example, potentials which look like this, and you can fill the sort of Fermi C, or you can put a different number of eigenvalues in one of the wells versus the other. And so this is a sort of spontaneous symmetry breaking phenomena that can happen at infinite n, that cannot happen at finite n. And what we see in this plot in green is the set of all exact solutions to this two-cut matrix model. And this, the fact that there's a curve and not a point is telling us that there is some sort of moduli, or there's some sort of filling fraction that interpolates between the left side and the right side. And that corresponds to, again, filling the eigenvalues with different numbers. Okay, so it's also interesting that in our model, what we see is that the constraints sort of smoothly find not just a single point here, which is the point where there's no symmetry breaking, but the model allows for the approach, the bootstrap approach, finds the entire line, which is allowed by a general filling fraction. Sort of more generally, this is a little bit of an aside. We can discuss what happens if we relax the positivity constraint. So if we just try to solve the single matrix model without imposing positivity of the eigenvalue distribution, we can find other solutions. For example, solutions that look like the one on the right, where in addition to having, this is sort of like a three-cut solution, where in addition to having eigenvalues at the minima, you might have some eigenvalues at the maxima. But if you look at these solutions more carefully, you'll notice that the eigenvalue density there is unphysical, it's negative, right? And you can see if the eigenvalue distribution is negative, you expect to find solutions because essentially the large N effective action looks like that of a bunch of charged particles which are repelling each other, right? But they're sitting in some potential. So if you reverse the sign of the charge, then a minima becomes a maxima, and a maxima becomes a minima. So a minimum here for the anti-eigenvalues allows for them to sit comfortably there. But of course, the solution is not physical in the sense that it involves negative eigenvalue distribution, which is not allowed. But notice that if we had relaxed that condition, we would get a bigger set of solutions. And that set of solutions exactly coincides with the dimension of the search space that we were discussing before. Okay, so the point is that the dimension of the search space can be thought of as the set of filling fractions before you impose the requirement that the eigenvalue distribution has to be positive. Now, this is a nice sort of simple story, but in the multi-matrix case, like I said before, we don't have an analog of the eigenvalue distribution. So I don't have a simple criteria like this, but it's nice to know what's going on under the hood, sort of, in the single matrix case. Okay, we can furthermore analyze why the method works so well as follows. So it might seem like a surprise that just imposing this very weak condition, positivity of single trace correlation functions, will be enough to actually isolate the exact solution. And we want to know, without just trying, infinitely many examples, whether or not this is a general thing, or is this a coincidence, or what. And here is sort of a intuitive argument for why you might expect this method to work in the single matrix case. So if you think about the constraints that come from positivity of this correlation of this cal-M, the inner product matrix, this is equivalent to setting all the determinants of this matrix, of the submatrices of this matrix, to be positive. And it's not so hard to see that you'll get some shape like this in the space of matrices. And this shape has the geometry of a cone, right? So what we're really trying to understand is whether or not the exact solution to the problem lies in the bulk of the cone, or whether it lies sort of at the boundary of the cone, right? If it lies close to the boundary of the cone, then we would be in luck, because you see, if you just guess the slightly wrong value of trace m squared or any of the values in the search space, if you're on the boundary, it's very likely that you will sort of penetrate the cone and go into the forbidden region. But if you're in the bulk, it's not so clear why that would be. Now, so that motivates us to think about why you might want to sit at the edge of this cone. And sitting at the edge means that there is an eigenvalue of your inner product matrix, which is rapidly approaching 0. Now, this might sound a little funny. Why do you have a sort of nearly null vector in the exact solution? And but actually, there's a very simple explanation. So if you think about the eigenvalue distribution in the single matrix model, one of the sort of obvious features is that it has compact support. And because it has compact support, we can find many polynomials which are approximately 0 in the region where the eigenvalue has support, but are non-zero outside. So in particular, as we increase the size of the matrix, as we increase the size of this inner product matrix, we are going up in the space of allowed polynomials of correlation functions, right? So as we increase, we're essentially allowing better and better approximations to the 0 function inside this eigenvalue region. So by finding these sort of nearly 0 functions, we can find an eigenvector of the inner product matrix with nearly 0 eigenvector. And it's clear that as we increase the degree, we'll rapidly approach the boundary then of the cone. So in particular, here are the nearly null eigenvectors for the quartic matrix model. The exact solution of the quartic matrix model, and you see that the pattern is what I just explained. In the case where there's a two-cut solution, for example, where the eigenvalues sit, in the 2 minima and they're separated by some distance, you see that the nearly null eigenvectors are exactly what you expect. They have some support outside of the region where the eigenvalues sit, and then they're almost 0 inside that inside the region where the eigenvalues reside. Okay, so this explains, at least in the one matrix model, why the method converges so rapidly, and why you might expect it to work in general. Okay, any questions about this? Okay, for the multi-matrix case now, we can discuss what goes wrong, or what happens. And it's, in general, significantly more complicated, but conceptually there's not much difference. So the technical complications are that the size of the inner product matrix is growing exponentially, right? The size of, in the single matrix case, for a fixed degree correlation function, the Gram matrix is basically proportional to that degree. Whereas in the case of the multi-matrix, it's growing exponentially. So we have to deal with very large matrices. That means that in principle, we will have to be able to diagonalize, or at least find the minimum eigenvector of the minimum eigenvalue of this very large matrix. And another separate issue is that the search space in general has a much higher dimension. As we saw from the estimates, it roughly grows exponentially with the degree of the polynomial which the multi-matrix interaction has. So in general, the search space is going to be much bigger, and that means that we're doing some sort of high-dimensional search problem where evaluating the loss function, or the function which tells you whether or not this point in parameter space is allowed or not allowed, is very expensive because it involves calculating the minimum eigenvalue. And it's also costly because there's so many directions to go in, right? There's also the issue of finding global minimum versus local minimum in the minimum eigenvalue space. So in particular, if you want to get the best estimate for some correlation functions, right, one strategy is to just do gradient descent or gradient ascent on the minimum eigenvalue, so that you find the point in the search space such that the matrix is the most positive, right? And that would be some, approximate answer for what you might expect the actual correlation functions to be. But doing that, we have to be quite careful that we don't just find some local minimum, but we, obtain something which is close to the global minimum. Okay, so just to illustrate how to do this a little bit in practice, we can discuss this particular matrix model, which has the following form. It's factorized in A and B, except for an interaction which couples A and B like this. Okay, so this is a simple model which is not believed to be integrable for a general choice of W. W here is just a polynomial in A's and B's. And it has a Z2 symmetry, which allows us to simplify somewhat the search space, right? We only need to consider correlation functions which are not related to each other by some Z2 symmetry. Okay, so in particular, we can consider the case where W is just some cubic polynomial, right? In that case, the search space is only two-dimensional, and it's it's a rather straightforward thing to solve this problem numerically. And in fact, by some clever field redefinitions, you can relate, for the particular choice where you choose W to be cubic, you can relate this model to the Isin model in a magnetic field, and that problem can be solved exactly. So that can be used as further cross-check of this method. But you can also try a quartic potential, in which case there's no obvious way to relate this problem to any solvable problem. And in that case, the dimension of the search space is also significantly higher. It's 8-dimensional, but yet we can still solve it. So I will now try to explain this. And I should say that while I'm mostly treating this model as a proof of concept that this method works even for more complicated multi-matrix models that we don't know much about, I should say also that it might be interesting just to explore this model by itself. In particular, this model could have new multi-critical points, and characterizing them numerically would be sort of a very concrete, interesting thing, I think, to do. Okay, so if we focus first on the case where this potential W is cubic, okay, so the model is given by the expression below, we can see just how increasing the constraints in the search space works. And again, just like in the single matrix case, it appears that as you increase the constraints, the solution, the allowed region is shrinking to a point. So this gives us some optimism that even for the general model, there's a convergence of this method to the exact solution. This gives us some optimism, despite the fact that I don't have an argument like the nearly null vector stuff, which explain why the single matrix model algorithm worked. In the second plot, I'm choosing to enforce all correlation functions, whereas in the first plot, I'm enforcing positivity of just some subset of the correlation functions, like the ones which just involve a squared b, like a to the k, b to the l, as opposed to arbitrary insertions of a and b's. But it's just some technical thing. The main point is that as we increase the number of constraints, again, we get convergence to a nice point, and that's consistent, I think, with the exact solution obtained by the redefinition to the Isin model. Okay, another interesting thing that we can do is we can try to find the critical point. So this plot, unlike before, where we were increasing the number of constraints, here in this plot, we're holding the number of constraints fixed, and we're simply asking what happens as we increase the coupling. And we're increasing the coupling in some correlated way, because there are actually two values of the coupling, right? So as we increase the coupling, we see that these contours are shrinking. And again, they're shrinking not because the constraints are becoming tighter in the sense that we're adding more constraints, but they're shrinking because the model is becoming closer and closer to the critical point and perhaps passing it, so that it's more and more difficult for the model to be consistent, right? The difficulty of the model being consistent translates into shrinking of the contours. And the point at which the contours shrink to 0 gives us an upper bound on what the critical values of G and H, such that the model is ill-defined, right? So in general, we could imagine just taking some arbitrary multi-matrix model, which has many couplings, right? And tuning the model to the critical point by using this algorithm. And we could then map out the critical surface in the space of model parameters. And this is something which I hope to be working on in the near future. Now, we can also explore the quartic model. In the quartic model, the main point is very similar, but the main point of doing this is because we don't expect this model to be integrable, unlike the previous case. And in this model, you see something very similar. So in this case, I'm plotting a trace A squared as a function of trace A. So the search space, on the other hand, is 8-dimensional. So I'm only plotting 2 of the 8 dimensions, and I'm marginalizing over the other 8 dimensions. So here we're plotting the different constraints as we increase the size of the matrix. So already with basically no input from the loop equations, we know that trace A squared has to be greater than trace A quantity squared, right? That comes from the determinant of a 2x2 matrix being positive, right? That gives us a quadratic relation, which tells us that trace A squared is greater than the quantity trace A squared. So that's this curve, right? And then as we put more and more, I see that this is slightly mislabeled. This should have been d equals 15. For d equals 15, we have this rather large green region, but as we increase the number of constraints, we see again that the region is shrinking, and it's shrinking to a critical point. And I believe, although this hasn't been checked extremely carefully, I believe that this convergence happens in all dimensions in the search space, not just the 2 dimensions that I'm showing. Okay, I also want to emphasize that these matrices are extremely small, like by any computational standards. I'm only trying to diagonalize a 35 by 35 matrix, and already we're getting some sort of very interesting constraints that for a general matrix model, I would have very little idea about how to obtain such results. So I think that this is quite promising. There's nothing in principle stopping us from considering much larger matrices of inner products, like 1,000 by 1,000, or 10 million by 10 million, or I guess 2 to the 16 over 2 times 2 to the 16 over 2, or something like what we might be on the verge of being able to do with more powerful computers and GPUs and all that stuff. So I'm optimistic that if we really want to nail down some particular model and, for example, try to extract its critical exponents and things like this, that these things should be accessible as long as we are able to scale up the algorithm to work on bigger computers. But that's just some technical problem that is conceptually rather straightforward, at least. Okay, some future directions for this approach. One I've already been emphasizing is searching for new string worldsheet theories, but this is just an application of the approach. There are potentially many other applications. And I would be interested, perhaps many of you have some applications of multi-matrix models that you've encountered that you would like to perform. It'd be interesting to try them out. The second thing that we would like to do is to extend this approach so that it works in the case where there are fermions, and more generally in the case where the measure is not positive. So in that case, it's not 100% clear what the requirements should, the positivity requirements should be replaced by. But perhaps in some special cases, you could integrate out, for example, the fermions and get some positive determinant, but those are probably some special cases. Another direction is to try to compute 1 over n corrections. So far, I've only been discussing the strict large n limit, not even 1 over n corrections. And it would be interesting to try to compute these using an approach inspired by positivity. Of course, we would also like to generalize to higher dimensions. So some even one dimension is quite interesting because there's the C=1 matrix model, there's the BFSS matrix model, there's the BMN matrix model. These are sort of interesting models that we would like to solve, but well, at least for BFSS and so forth, we'd also need to solve the fermion problem. So it seems like there are several things that would need to be solved, but you know, in general, any technique that can help analyze a strongly coupled large N system seems like something that we should think about. And of course, the very distant dream is that we tried to solve something like large N QCD. Okay, I don't have any comments about that. Now, some technical questions, of course. Can we estimate the dimension of the search space better in some examples? Can we prove that the matrix that this method, the bootstrap method, converges in the multi-matrix case? And can we quantify exactly how fast it's converging? That would, you know, the hope would be that we could use some sort of argument like the nearly null eigenvalue argument, except adapted to the case where we don't know the exact solution. And then, of course, there are a ton of practicalities about how to scale up the algorithm so that it works when you have a completely general matrix model, and you have, you know, 50,000 parameters, and you know, you're trying to diagonalize million by million matrices. But these are just some practicalities. Okay, so I think that's what I had to say. Thanks for your attention, and I'll be happy to take any questions.
I have one quick question. So if we go away from the infinite N limit, how does the search space become bigger if we include if we take into the finite N correction?
It's not clear to me in the yeah, it's a natural question that I don't know the answer to.
Okay.
Especially in the multi-matrix case, I don't know the answer to that question.
Thank you.
Can I ask a question? So if you consider the lattice gauge series of the lattice of finite size, then in principle, it's like a multi-matrix model. So
sorry, can you repeat the beginning?
So if you consider the lattice gauge theory,
lattice gauge theory,
and take the size of the lattice to be finite, then
right.
In principle, it's like a multi-matrix model. But now you need to deal with like unitary matrices rather than Hermitian matrices.
Yes.
So I guess like in that case, like your method like works straightforwardly.
Yeah, I think if you have unitary matrices, yeah, you just consider, yeah, exactly. You just consider, you still have some positivity requirements. The positivity is, yeah. Right. Yeah, as long as you definitely have the loop equations and you still have positivity requirements. So I would expect that the method would still work. I haven't checked it, but yeah, I mean, for example, the simplest thing would just be like a one-dimensional lattice theory, right? So you just have like C=1 matrix model on a, you know, on a line, on a circle, but you discretize the circle, right? And then that's like having a bunch of matrices coupled to their nearest neighbor, right? And that model is, I suspect, can be analyzed. I mean, that model would just be like some, you know, you have some trace AI plus 1, and then you have interactions of this, you know, to a general potential. I think that model could probably be analyzed by this method, at least for small number of lattice sites. I don't know. Yeah, I don't know how feasible it is in practice to analyze such a model. Yeah, I think
I have a question about the behavior you found. So you found some feature at the point where the potential curves and the matrix, the finite N matrix does not converge, right? That's in the one end. Right. Now, but then you also consider the double cut, which exhibits the Gross-Witten transition. Now, here there is critical behavior when the two cuts approach each other, but the model continues to make sense.
Yes.
Do you see any difference between these two cases? So fundamentally, from the point of view of the integral, they're completely different.
You mean like, is there some sort of kink or something whenever there's the two cuts merge?
Right. When the two cuts merge, there's some singular behavior, but you can continue and the model makes sense even beyond that point. In fact, the finite n interval makes sense. That's not the case in the other.
Right, in this peninsula plot. Yeah, that's a good question. Well, my answer is that I haven't checked that, but I do think that in principle you should be able to see it, although in practice. So let me tell you about some other model, which I think is morally similar to what you're asking, but not quite the same. So if we just look at the Isin model, right? The Isin model, you can study it certainly at criticality or not at criticality. So you've tuned G already so that you're in the limit where the planar diagrams are large, but you haven't tuned C in any particular way, right? And it's only at some value of C that you get the actual Isin minimal model, right? And if you look at the plot in parameter space, there's a kink at the location where that special value of C. Obviously, the model is well defined whether or not you go to the left or right of that kink, but there is a little kink there. But the kink is not in the first derivative of the curve. So if you want to see the kink numerically, it's a little bit challenging. You have to have a really precise map of the critical surface so that you can extract the kink. Is that relevant to your answer, to your question?
I think so. Yeah.
Yeah.
Thank you.
Yeah, I think it's a good point, though. In particular, in the single matrix model, we can analyze everything very easily with it doesn't involve diagonalizing big matrices. It just takes maybe 10 seconds on Mathematica. So yeah, it'd be a good exercise to do.
I should point out that if even within one cut, as opposed to two cuts, you can still have potentials that make sense by going to higher power. So if instead of going to, say, 6th order potential, instead of going to 4th order, you're going to 6th order, then there's an inflection point. And with the eigenvalue density, the corrected one with the Coulomb potential, at that point is critical behavior. And that's known as a minimal model coupled to gravity. I think it's Li-Yang coupled to gravity. The potential there makes sense for both values, both before and after the singularity, but there's a singular point in the middle. So it's a simpler case than the two matrix model that you mentioned.
Yeah, I agree. Yeah. I agree. In general, we could try to have a qth order polynomial and then try to find, do the tuning right so that you get the 2, q or whatever minimal model. And yeah, I would like to see that you can extract reliably, say, the string exponent from using this method, but that's something I haven't done. Yeah, it's a little tricky, of course, because you're trying to fit, in order to extract the string exponent, you have to fit a power law. And, it's the usual issues of fitting a power law when you don't have infinite precision. So, so either you could try to extract the power law by just brute force, by just going to really high precision, or you could try to do it being more clever. But yeah, I think that's an interesting question. And if, for example, you just play around with some general multi-matrix model and you find a critical point, obviously you want to start extracting critical exponents, and to do that reliably is obviously an important thing. Otherwise, we won't know anything about its continuum theory. So.
Presumably, if you learned how to compute connected correlation functions, you could find the singular behavior in the connected correlation function, which could be like in the 3-point function, for example.
Right. Yeah. So that would involve computing a 1/n correction, which I think is in principle doable. Like at 1/n, so I can say a few words about 1/n corrections. For 1/n corrections, you still have the loop equations, obviously, and you still have positivity, and both of them are enhanced slightly. So the loop equations, you don't have the factorization, but you have some corrections. And positivity, you also get corrections because there are sort of non-trivial positivity relations amongst double trace correlation functions. that aren't there just for single trace correlation functions, right? So basically, it's the statement that, for example, trace of m squared is positive not just on average, but including fluctuations. So there are some slightly stronger requirements. Now, I think in the single matrix model, at least in the one-cut solution, once you know the eigenvalue distribution, you determine all the 1/n corrections just by the recursion relations. So you don't need to consider those if you accurately get the if you can accurately extract the eigenvalue distribution, you don't need to consider any further constraints. But I'm not sure if that's the case in multi-matrix models.
I didn't quite understand if your search space was of arbitrary size in the case of the two matrix models, or if you had distinguished search spaces.
The search space, I think, is defined to be the minimal set of correlators. So it's the actual correlators that you choose are arbitrary, but I think the dimension of the search space is not arbitrary, and it's some fixed number that's model dependent. So for example, in the Isin model, the search space has dimension 2. And for example, you can take as a basis trace A and trace A squared. Once you know trace A and trace A squared, I believe you can determine all correlation functions from these two values. Or more general,
in a two matrix model, I'm surprised there's anything as simple as that, because you can have a correlator that's a very complicated word in A and B. Are you sure there's an algorithm to determine it in terms of finitely many traces?
I'm okay. I had this crude argument for why there should be a finite number, and so indeed I was extremely worried about this in the beginning, but empirically it seems to be finite, and somewhat less empirically, there's this crude argument where although it's true that the number of correlation functions is growing exponentially, it's also true that you see the number of loop equations is also growing exponentially, and it's growing exponentially at a rate that is slightly faster. Well, the number of loop equations is m to the k, whereas the number of correlation functions that you introduce is m to the k plus d over k plus d. So there's a value of k where the number of constraints and the number of unknowns is balancing. So at this point, you would expect that you don't need to introduce any further basis elements into your search space in order to determine the rest. But I agree that this is a little bit surprising. I mean, this is only a parameter counting argument, so there could be degeneracies, and in practice there are degeneracies, and I don't know how to get a precise counting. But empirically, what I mean by empirically is if you just write down a bunch of loop equations for the multi-matrix model, and you just start with some small search space, you will find that you're able to determine all the rest in the models that I considered.
Okay, thank you.
Can I ask one more question? So,
sure.
So could you elaborate a little bit about the positivity requirement for the non-planar corrections? Because like if you expand everything like in powers of 1 of n, you get the leading term is something positive plus like a 1 of n times some number. But because 1 of n is very small, like it seems to me it's very hard to constrain what those numbers are.
Yeah, I agree with that. I agree with that. But for example, well, here's a simple example, right? Let's say you're computing the quantity trace m. Okay, let me get some clear paper. Let's try this. Okay, hopefully you can see this. I think if we, oops, okay, this may not work. Well, okay, I'll just say it in words.
If you click on share screen, there should be a whiteboard you can use.
Let me try. Okay, I think this might work. word. But let me just say it in words. I don't think it's worth it. If you consider the quantity trace m squared, and then consider the double trace version of it, right?
Mm-hmm.
So basically the statement that I'm trying to say is let x, you can probably see this, let x be the quantity trace m squared, right?
Mm-hmm.
That x is a positive random variable, right? Whether or not, by positive random variable, I mean it has no support in any part of the real axis that is below 0, right? So in particular, the quantity x squared minus, the expectation value of the quantity of x squared minus this quantity that I'm highlighting right now, right? This quantity is 0 to leading order in 1 over n, but it's leading order in 1 over n. So the leading non-order, yeah, the leading non-trivial contribution is 1 over n.
I see.
There's some constraint that this has to be positive.
Oh, I see. That's very nice.
Yeah, in general, if you have a positive random variable, you can ask the question, what constraints does it have to satisfy? And that's related to the hamburger moment problem, but it's actually called the Stieltjes or something moment problem, because there's this additional constraint that x itself has to be positive. So it turns out that not just the inner product matrix of x has to be positive, but if you include, basically put some offset. And so there are two matrices which have to be positive, and both of those matrices, if they're both positive, then you're guaranteed to have some probability distribution which has support only on the positive real axis as opposed to the general real axis. So yeah, there's these old like 20th century mathematics results which in principle would determine these. So this is just one example. This is the most simple example, but you know, this comes from the determinant of some 2x2 matrix being positive. But in general, there are some polynomial relations between moments like this. Yeah, I'm not, yeah, the practicality of exactly how to implement them and how to implement them efficiently, I think is an important question if we want to compute one over n corrections. And I don't have much to say about this.
Question. Hi. Have you thought about adding also, say, double trace term to the matrix model?
Yeah, so
you have two separate terms like g trace m to the 4 plus g prime trace m squared squared. Because that has more subtle changes in critical behavior.
Yes, I didn't try to extract the critical behavior, but I did just try to see that for some value of g prime, that you get convergence to the exact solution, right? You know the exact solution because you can integrate out. You can introduce some auxiliary random variable. This is the trick that you use. So yeah, I tried that, and so I expect that the model should also work when you include double trace terms, triple trace terms, etc.
Okay. Yeah, that model exhibits a jump in string susceptibility also, maybe a bit similar to how you said the Isin model. That's some jump when you tune C. This one is probably a simpler version of that.
Right. Yeah, I guess even in the, yeah, even if you have some even potential, without tuning, you just get the, with just a little bit of tuning, you get the string susceptibility constant given by the 1 comma q, or, you know, sorry. Yeah, and with some more tuning, you get the higher critical points or whatever. We could try to do that too.
Is there any other question? Well, if not, let's thank Henry for a very, very nice talk. Thank you.
Thanks.